Hello, everyone. Thank you for joining us today. Welcome to the webinar on deep learning in microstructure analysis, real-world use cases. My name is John Sosa, and I'm the CEO and co-founder here at MIPAR Software. I hope everyone is staying safe and healthy out there, and I really appreciate you giving us some of your morning or afternoon or evening, wherever you may be. So today is going to focus on the use of the latest in deep learning AI tech, specifically how it relates to solving some of the more challenging but often commonly encountered practical problems in microstructure analysis in materials. We introduced deep learning into MIPAR back in around July of last year, and it really has had a profound impact on the types of problems that we can reach with the software and the accessibility of those solutions to the everyday user. We realize that in many labs and facilities around the world, there are approaches to quantifying microstructure today. Many of those approaches can involve a manual component. Sometimes they're purely manual. And what we've seen is deep learning has allowed us to take either archived, manually annotated microstructures or allow the user to continue the manual process for just a little bit longer, and then be able to take that input and evolve intelligent, automated solutions that work, that quickly replace that manual method. And this has been a real shift in how challenging automation is approached, especially in MIPAR. So that's going to be the focus of today, is a presentation of that workflow across a few different cases. So where I'd like to get started is by considering an example such as this one. This is a titanium microstructure. Specifically, we're looking at prior beta grain boundaries. So the area in here at one point at high temperature was all beta phase. As the sample was cooled down, the alpha phase precipitated inward, and you're left with these boundaries where a certain type of alpha has precipitated along them, thereby revealing them. But since the material is no longer entirely beta, we refer to this as a prior beta grain structure. And this is a particularly challenging problem to automate in that there is no intensity difference to be used with any sort of conventional thresholding approach. You have purely a texture-based feature detection problem, which our brains seem to be fantastic at recognizing, but historically has been immensely challenging to get software to recognize accurately and consistently. Now, this could be any challenging problem in materials, any problem where historic image processing approaches have failed to work. And in these cases, it is absolutely appropriate to ask whether at the end of the day, automation or the attempt to achieve automation really returns significant value versus just spending the time doing it by hand. I mean, I think we all recognize the immense potential of automation, the orders of magnitude time reduction, the reduction in user variability, the ability to obtain more complex measurements than are possible by hand. But I think we've all been in this position before, and I thought this was a very appropriate comic for this topic, where ideally we put in a bit of work early on to develop an automated approach to solving a repetitive task or project, and after that initial work, we nail the automation and we no longer have to do that tedious task anymore, and we move on to something else. Where all too often in reality, whether it's writing our own image processing scripts or trying to piece together a pipeline in a commercial product, we get off to a good start and then quickly realize it wasn't so simple. There are many iterations required, there are unforeseen challenges, and we end up getting lost in this pursuit of automation, and we don't even have time to do the task that we tried to automate at all. And we're sensitive to this. We understand that many real problems struggle to get over that activation barrier of, okay, I'm going to spend this time trying to automate it. And once we're a ways into that attempt, we realize we probably could have just done the thing by hand already. So how do we address this for these very practical problems that often present this reality? So again, when we look at considering automation over a current manual or even semi-automated approach, we're aware of the benefits. We get immense speed improvements, much more objective approaches to the problem, which is paired with a reduction in user-to-user bias. And to boot, our results tend to be much more traceable and auditable and defendable over time. But if these three requirements aren't met in trying to develop an automated solution, it's going to be hard to realize those benefits. Almost always, we need a solution in an automated sense that is as accurate or better as what we've been doing by hand. That solution can't just work for one image or one condition. It's got to handle at least a reasonable level of lighting, exposure, sample prep variation, and it can't require a computer science expert to put the solution together and maintain it. It's got to be something that folks that have been characterizing samples historically can move into and develop a solution that can be used throughout an organization. So historically, before even the advent of more graphical processing applications, we were writing code for each problem. And in many cases, that's still the approach. So if we consider for a moment this very rudimentary plot of two axes where you've got a solution that ranges from requiring tons of experience to very little experience on the x-axis, and one that is not robust at all to very robust on the y-axis, I think it's reasonable to place many of our hard-coded solutions in an area like that. They clearly require a wealth of expertise to develop and operate, and typically they're pretty tightly tuned to a specific problem with hard-coded settings and thresholds and other things that make them fairly inflexible, or at least very difficult to adjust to different conditions. What we have been able to achieve with MIPAR over the years has been to move into a realm like this, where what we call recipes, which are graphically built, very interactive, infinitely adjustable algorithms that require no code to develop, they're able to lessen the learning curve, lessen the experience required to build and operate, and are able to get us oftentimes to a more robust solution because of that interactivity and that ability to add numerous steps that can accommodate different conditions very quickly. We get to an area like this. Now for the simpler solutions, this often works very well. Because they're simpler, you usually need even less experience to build them, so that dot would move more to the right. And because they're simpler problems, the solution doesn't need to be very robust. So getting somewhere to the middle of the robust scale is perfectly acceptable. However, as is the focus today, many of the common real world problems still fall outside of this solution space where you need a significant level of robustness, and they're simply too challenging for the average user to automate effectively. And this is where we feel deep learning really places us. It's really a privilege to be working at this time period where we've seen this breakthrough technology, which is rare to see, where you end up working with something that somehow allows you to develop even more sophisticated solutions while at the same time needing less experience to do so. That's somewhat of a almost a too good to be true scenario, but we have seen through our deployment of it that it is very much true, and that's what we're going to be taking a look at today. So here's what we're going to do. We're going to go ahead and go back to that problem, and before we get into some of the other cases, we are going to break out into the MIPAR software, and real time we're going to set up a tracing. We're gonna demonstrate how this microstructure was annotated, and then we're going to start a training live. It's going to run in the background while we present the rest of the webinar, and then by the end it'll be done. We'll take a look at how it did. So let's break out into MIPAR and have a look. So here we are in the deep learning trainer application of MIPAR, and we'll start by just dragging in a couple of the reference images that we're going to use for training. And we can do our tracing directly in this application if we want to. We can add a layer, call it boundaries, and take our pen tool and just start tracing. And we could get through this fairly quickly. But what we actually did in this case was drop these images over to an iPad, use any of the number of tracing apps that are available. You can use the built-in markup application. We use an application called Procreate that we like. And it's a very natural, much more enjoyable experience with the Apple Pencil and the iPad tech these days to just do your annotations on something like that, and then you can import those right over into the training environment. So what I'll actually do is just go grab those tracings that we've made. And there we have our boundary tracings that have been done. And 2 classes at least are needed for deep learning training. So next to the plus button for adding layers, we have a handy tool that allows you to take all the tracings that you've done. If you've only done one class and you'd like to train that plus basically the inverse of that, then you can add an inverse of all layers here. We'll call this the interior class. And now we've added that, so we're set up for training. Here, I won't touch too long on the settings. They're described in the user manual. Basically, the first one here, tiles, allows us to split up an image into several subfields. We found this not only reduces the memory demand while training, but produces better results, since deep learning training tends to be fairly image hungry, although we've gotten great results even with just 3 to 5 images sometimes. The size factor for this size image can be kept at 1. This ranges from 0 to 1, and it's just a degree of downsampling that's done, again, to improve performance and reduce memory load. And then the epochs here are really just a unit of duration for how long the training is going to run. We've got a chart in the manual that makes some recommendations for the number of epochs based on your other settings here and how many images you're using. We can run this for 500. And then just the processor to choose. Now for deep learning training, a GPU is strongly recommended. You can train on the CPU, you can apply on the CPU. For training and applying, the speed up on a GPU is usually 8 to 10 times what you get on the CPU. So for training, when you're talking about minutes to hours, something that would have taken a whole workday on the CPU can be done in under an hour on the GPU. Whereas with applying, you're usually looking at seconds. So you'd be looking at, 10 seconds to apply the model on the CPU versus a second on the GPU. Still a nice speed up, but not as much of a deal breaker as training can be. So again, in the manual, we have recommendations for different pieces of hardware for training. This particular workstation is using an NVIDIA RTX 2080 Ti. So we'll go ahead and get started. So we'll hit train new. It's going to break up our image into the tiles, initialize the training, get started, and give us an ETA here on the training. So we'll let that go, and let's get back to the slide deck. So let's get started with the twinned grain case. This really can just be a stand-in if you want it to be for any challenging grain detection problem. There are dozens, if not more, but this does represent one of the most challenging grain recognition cases we've encountered, where it's almost easier to find the twins than it is the grain boundaries. You've got just a very strong dependence on local pattern difference that tells your brain when to move from one grain to another. If you've had experience in looking at this type of microstructure, you can recognize the grain boundaries, but you've got to do some mental gymnastics behind the scenes and piece together a lot of these, striped features into a typical grain shape before your brain recognizes, aha, that's an entire grain right there. And we've tried all kinds of approaches prior to deep learning, never came close to getting the software to do what our brains are doing. So historically, this has been done purely manually. If you're just looking for a mean grain size, folks will lay down a set of random lines and count off the intercepts and get a mean size that way. This particular client needed a full size distribution, and even though going with EBSD would have been more unattended, the time cost and sample prep challenge involved caused them to just sit down and trace all these boundaries by hand so that they could get a full, grain per grain size distribution measured. We've talked about the challenges here. You've got, low contrast in some areas, of course, like almost every problem seems to have to one degree or another, but then just very challenging local morphological changes are what your brain is picking up on to differentiate these grains that somehow we have to teach the computer how to do. So let's just break out into the software and take a look at what the previous state of the art used to give us, and then how we were able to take the tracings that were already available and evolve them into a next-gen solution. So we're back in the deep learning trainer here, and let's open up the session file that was used for this training. Again, this client had tracings of these structures that had been amassed over the years. We chose 3 images, and here we have the boundary class in red and the interior in green. And we used, I believe when this was actually run, we were looking at about a 5x5 grid, no downsampling, and 500 epochs. This was run, it took about 30 minutes to train. Then we can take a look at the solution. Now we'll take a look at the solution initially on the images that were used for training, but then we'll make sure to look at cases where we'll look at images that weren't at all part of the training set, since that, of course, is always of primary interest, is how well this tool can learn and apply to images that it never saw before. So let's go in first to the image processor. And what we're going to do is take one of the images that were used as part of the training and just take a look at how that performed with the previous state-of-the-art solution. So this is the best we could do with MIPAR prior to deep learning. It involved a combination of edge finding filters, artifact rejection, trying to absorb some of the twins into their parent grains if they were very, elongated or not. But we weren't able to come up with something better than this, where you're finding all the boundaries fairly well, but that's not the point. We want to be finding only the grain boundaries, not all of these various twin boundaries. And quite honestly, I never thought I would see an automated solution to a problem like this. But let's go ahead and drag in the deep learning based recipe and see how that performs. So this, of course, blew us away when we saw it. It does a remarkable job detecting the various boundaries and ignoring the twins. The blue grains here on the edge are ones that contact the edge and are therefore not used in measurement. But that's it. That's the classification of the edge and the full grains. You see the mean diameter pops up here as it's part of the recipe. Now, there sometimes can be a need for some minor corrections. The way this recipe has been set up, you can make those edits. Let's say you wanted to fill in this boundary here, if you consider that to be a boundary. And the way this is set up, you can make the edits quickly, and MIPAR will clean them up for you. You just draw a line like that. You don't have to be perfect. It'll fill that in, clean up the edges. If there was a boundary you didn't want, one that was a false boundary, we'll have to look for one here. Up in this area, there's one. You can just take the erase tool, just cross it out, and it'll disappear. Now you can use, if you find yourself doing that frequently, you can take those corrected results and update the model with them, retrain with those corrections so that the algorithm learns from those corrections. So let's take a look at a quick measurement. The recipe is aware of the scale of this microstructure or of this image. So we have the scale factor up here so that we can measure in physical units rather than pixels. You saw the mean grain size pop up when the recipe was run, and that of course can be regenerated now that corrections have been made. There's barely any change. If we want to look at a full distribution, we can just push play. And not only is that going to give us a grain size distribution here, but it's color coded to match the different objects in the image. And there's a nice correlation between all three of these graphics. Let's say we sorted by diameter, so we look largest to smallest. Click on a cell here, that grain is highlighted in the image, and you can even drop a line on the histogram where that sits. You can march down the histogram like this. It works the other way, so you can click on a grain, and that cell is highlighted. You also see where it is on the histogram. So a nice explorative environment here. You get your stats, mean, min, max, standard deviation. We can generate a report. Click print report. Fill out your information. This will be stored and reused the next time. And this will then auto-generate a Word document formatted with these graphics in place as they were configured in the window And then this can be further edited, exported to a PDF. The basis of this template comes from a Word template that is stored in your installation directory, so you can modify that to add your own logo, make other customizations. And if you did want to change settings in here, you wanted to, say, adjust the color scale limits, maybe you wanted to use a different color map, maybe you wanted to change the number of bins or custom set them to certain ranges, all of that gets resaved when you click Save Settings. So the next time you or a colleague were to run this recipe and you push play, all of that measurement configuration comes right back for you the next time. So that's generating some measurements and processing a single image. What about batching? What about how this recipe performs on not only the other training images, but one that wasn't part of the training set? Well, let's go ahead and just drag another one in that was part of the training set, say this one here. Going to reload the recipe, but I won't save any of those changes that were made. So that opens up, recipe reruns, you get your detection, get your measurements, push play again for your distribution. Could do it another time. Fairly quickly to move through images and survey the results, see how the recipe is working. Maybe if you only have 5 or so images, that's the workflow that you need. But we can take it a step further and run it fully unattended. So let's go ahead and do that. We can just launch the batch processor. You get a recents drop down. Your last several recipes that you've loaded are set there. And that same menu is available here. So you can easily just choose your latest Twins deep learning recipe. And then let's drag in the images. So we're going to drag in 4. It's going to auto set the place to save them right where those images are loaded. Click process. And that'll move through and apply that recipe to all 4. When it's done, hit view results. Now, by running the recipe, we already have a measurements spreadsheet waiting for us. There was a measurement in the recipe. So here in the output directory, we have a CSV file that has the mean of each image. If we had asked for the other stats like min, max, sum, standard deviation, those would be here as well. But if this is the report that you need, you just want to look at a mean grain size per image, then there you have it. But sometimes even if that's all the measurement you need, it's still very useful to supervise what was actually measured rather than just taking a spreadsheet and running with it. So by clicking view results, that has opened the results of the batch here, and you can flip through, see how it did, maybe make some corrections if needed, and then either regenerate the measurements if you needed, if you had made corrections, or what a lot of folks end up doing with a batch process is aggregating the statistics from all fields into a single distribution. There have been times when folks thought they had to stitch fields together just to collect enough area for their statistics or to adhere to a standard, but then they end up with an unwieldy stitched image, and sometimes the stitching isn't perfect at the boundaries, and all they really needed was a series of fields as long as they could collect the data from those fields together into one distribution. Well, within here, now we can click Measure Features, choose the diameter measurement that we want to make from the size panel, and just hit View Measurements. We're just going to measure the complete grains. And this now is going to measure each field. It's going to group all grains into one table. And if we pick this column, now we're plotting a grain size distribution across all 4 fields into a single plot with a single mean and the other stats. Again, you can generate a report out of this data, click print, and we'll get the representative image that we have stored back in the post processor and the rest of the results. Now, I'd like to point out that this image in particular was not part of the training set. This was a test image that did not contribute to the initial model training. And this is exactly what you want to see, where you have quality detection outside of the training set as indication that the model has learned enough to recognize the microstructure the next time it sees it. Of course, the engine is only going to learn what you provide it. So we recommend that you show it extremes if you have very different microstructural cases, you have different lighting conditions, prep conditions. Make sure that it is aware of the potential variation it can see. Again, that can happen iteratively over time. If you remember in the beginning, we started a training on this prior beta grain structure where we used an iPad to trace the boundaries here. And we did so on 2 fields of view, and we clicked train, and we had an estimated training time of 15 or so minutes. So now let's take a look at what we got. So here we are back in the deep learning trainer. The training is finished. And now we can save and apply the model directly. So we'll first choose a location to save the model, and then this will auto open the image in the image processor, load in the model, and show us what we have. And there we go. That's looking rather nice. Again, the bright pixels indicate the high probability of belonging to prior beta grain boundaries. And as we saw with the melt pool case, if we accept the model, that will add that application as the first step in the recipe. And now we can add a few extra steps to take this computer prediction and turn it into the final selection. So I will load a recipe which does that, and we'll see the subsequent steps appear below. So we see now the added steps below the deep learning application. Let's switch this final view here to a binary view, and we can now go back and look at how we had our original probability map that was evolved to the final selection. So from computer prediction to feature detection. Looking at the actual steps that were used at the end of this chapter, which is what we call groups of steps, we did a selection on the probability map to determine above what percentage of confidence we wanted to select pixels that sat on the boundary. This chapter removed artificial selections to reduce noise and produce a clean boundary detection. This chapter here connected those boundaries. And then this last chapter cleaned up those boundaries into thin lines. And that's our detection. Now we will just set a couple of layers. Our final selection we'll call grains. Perhaps we want to reject edge features. There's only a couple of fully contained grains. Call that whole grains. And this one here, this particular step rejects grains that are below a certain size. That can be in pixel area, that could be in micron diameter, but we could flag that and call it min size. And now with steps set as layers, when the recipe loads, you'll see it in this view initially, simple mode, where you'll just see the layer names and colors and key settings that have been exposed to the end user if you'd like them to be, where they have easy control over variables like min allowable grain size. Let's resave this and try it on a different image, one that was not part of the training set, like this one. And even with these deep scratches and boundaries like this, that on an image that was not part of the training set, I would say that this algorithm learned remarkably well how to detect what not too long ago I thought was an impossible problem to automate. So we started the training at the beginning of the webinar, and we had a fairly breakthrough solution done by the end. Now we could add some additional, we could look at ASTM grain size to finish this one off. We have the scale factor calibrated. If you have an image with a micron bar on it, doesn't have to be the same image, just needs to be one at this mag and resolution. We open over 150 different formats. Some of those are rich formats that have metadata embedded that can often bring the scale factor with them after they've been saved off the microscope. So knowing that scale factor, we could use rotating lines to conform to the ASTM E112 standard and output an ASTM grain size number. Now you could run that on both partial, edge contacting grains and whole grains. For this demonstration, the fact that significant portions of the grains are exposed and there really aren't many fully contained ones, we can just choose to run this on the on all of the grains. And there we have a ASTM grain size measurement. Lastly, let's run this on another image that was not part of the training set. And in my view, that's worked out very nicely. So we've seen the deployment of a very powerful technology that allows great accessibility to take expert input from metallurgists and microscopists, continuing to do what they've done for so long by manually marking up their images, and then allow this deep learning training engine to take over from there, learn from it, automate what used to be impossible problems, and we've been able to do so during the course of this webinar. So I wanted to finish with an overview and a reminder of just a few of the different project and material solutions that we have offered. Again, this is just a portion of the list, but you can break it down into the different types of analysis that you might want to do, or you can break it down by the different types of materials on which you want to perform that analysis. You can see phase analysis across all of these materials. You can see grain size analysis across all these materials. But we wanted to present the different solution opportunities two different ways, depending on how you characterize your application. And finally, what should you do if you'd like to learn more? If you'd like to explore whether these solutions and this technology are a good fit for your applications. Right now, you should be seeing a pop-up window that says request download. We have a few additional application slide decks over a few different areas that are available to you. If you click request download, you'll be taken to a page where you can specify which decks you'd like to download and optionally tell us a little bit more about your needs and what brought you here. You are welcome to share these decks with whomever you wish. You may also submit an image through our website, and this will go directly to our application specialist team, and someone will be in contact with you shortly to discuss in more detail whether MIPAR might be a good fit. And you, of course, can always email us directly at support@mipar.us or give us a call. We'd be more than happy to discuss your projects. Our team works very hard to transition and carry through expert support all the way from the early evaluation stages to the long-term client relationship stages. It often begins with an initial set of solutions aimed at addressing your immediate needs, but then commonly we continue to be available into the future as new projects emerge and you might need additional solutions. The software can be configured as much by the users as by us. It really depends on your in-house availability and your ideal workflow, whether you'd like to take our self-learning courses to become more comfortable with the product or gain expert training from our team. Those are certainly available for the folks that want to be more self-sufficient with the platform. But if you are the type of user that wants to have our experts on demand into the future to develop more solutions as needed, that is also a perfectly acceptable model. So thank you all very much for your attention. We'll transition now to the Q&A portion where we can review any of the questions that came in that were not addressed in the chat window and talk through those live. So if you give me just a moment to review the questions that we didn't get to, we'll move through those.